Welcome back to the deep dive. Our mission, as always, is to take the most complex technical specs, lay them all out, and give you the definitive intelligence report you need. And today, we're not talking about a new consumer EV. We're getting into the literal grit and noise of heavy-duty engineering.
That's right. We are going deep, really deep, into the 400-volt high-voltage system architecture for a P2 hybrid cement mixer. And this isn't just about saving a bit of fuel. It's about solving a really critical, almost absurd inefficiency problem.
Okay, let's unpack that absurdity right there. I mean, our sources are really clear on this. You've got a massive thirsty diesel engine, maybe pushing 300 kilowatts, and it's just sitting there on a job site, idling, burning expensive fuel, pumping out particulates.
All to deliver what? Maybe 25 kilowatts?
Yeah.
Just to keep a drum of concrete spinning?
It's a textbook case of terrible energy management.
Precisely. And that gross mismatch between the power you have installed and the power you actually need for the job. It's just unacceptable, especially as global regulations get tighter.
Right, you've got EPA Phase 3, you've got Euro 7 on the horizon.
Exactly. The industry mandate is clear. It's moving toward zero-emission, low-noise operation whenever that vehicle's stationary. The job site is becoming an electric zone.
So for you, the executive who has to roll out this next-gen asset, our job today is to provide that definitive McKinsey-style technical specification. We're basically laying out the architectural blueprint for integrating a P2 hybrid chassis with a 400-volt electric power takeoff, or ePTO superstructure.
And this deep dive will provide the actual engineering deliverables. We're talking schematics, design guides, component reports, everything you need to go from a concept on paper to mass production.
Okay, so let's start with the foundation of this whole thing, the core architectural logic.
It's all about the absolute segregation of power and control. We're using a dual platform logic. 400 volts is strictly for the heavy lifting, the high power tasks.
So traction assist and actually mixing the drum.
Right. And the 24-volt system, that remains the control area. It handles all the safety functions, the VCU logic, the communication buses, the monitoring, everything.
And that separation is critical, I assume.
It's non-negotiable. Because if you have a catastrophic high-voltage event, it must never, ever compromise the low-voltage system's ability to control core safety functions.
Things like steering, braking, and the critical interlocks we're going to talk about?
Exactly. Safety first, always.
Okay, let's start with the strategic advantage of this design. Why a P2 hybrid? Why not, say, a P3 or a full EV for this kind of vocational truck?
It's the sweet spot. P2 is really the sweet spot for heavy-duty retrofit and integration. It maximizes your efficiency gain with minimal intrusion into the existing drivetrain.
So you're placing the electric motor, the EM, right between the engine and the transmission.
Exactly. And the KZO clutch, which sits right between the engine and that electric motor, that is the technological pivot point for the whole system.
The pivot point, because when that clutch disengages,
The enormous diesel engine is mechanically and electronically isolated from everything else.
that decoupling seems absolutely pivotal. For our client, that means you can just shut the engine off. It changes the entire emissions profile at the job site.
It does. The engine only needs to run when you're actually hauling concrete from the plant to the site.
So think about that duty cycle.
Right. The mixer needs continuous, low-speed rotation, maybe 2 to 10 RPM, for hours. During transit, while waiting, during the unload.
Previously, that was all just an idling diesel engine.
Now the P2 system steps in. During transit, the motor gives you torque assist, which lets the engine run in a much more efficient zone.
And during braking, that's where the regeneration comes in.
Critically, yes. During braking, that P2 motor flips and becomes a generator, a kinetic energy recovery system, or KERS. And in a 40-ton vehicle, the amount of kinetic energy you can recover is immense. It dramatically improves the whole cycle's efficiency.
And then it gets to the site, engine off, and the 400-volt battery takes over through the ePTO. What's the advantage there beyond just zero emissions?
The main technical advantage is wiping out huge hydraulic losses.
Ah, the old way of doing it.
The legacy systems, they use a pump driven off the engine, high-pressure lines, a hydraulic motor on the drum. You can lose upwards of 30% of your energy to heat and friction.
So this is just a much more direct, more robust way to do it.
Far more. The new power loop is simple. You have the 400-volt battery, what we call the RESS. You have the P2 drive unit, which is the motor and its inverter. You have a specialized ePTO drum drive motor and its control unit.
And you need something to keep the 24V system alive.
And that's the high-power DC to DC converter. It keeps that 24-volt control bus powered up.
So we have the architecture. Now let's talk regulations. We need to establish what you called a highest common denominator baseline.
You do. because the standards vary globally.
The sources point out that while something like the UN ECE R100 sets a decent technical foundation, it's really the Chinese GB standards that are pushing the most aggressive thermal safety
It's
requirements.
absolutely right. UN ECE R100 is.
Yeah.
It's the baseline. It covers mechanical shock, fire resistance, overcharge protection, standard stuff.
But China's GB 3831 2020, that takes thermal management to a whole new level.
It really does.
It mandates 5 minutes of thermal runaway pre-warning time. Now, that sounds a bit arbitrary, but it serves a very specific purpose, right?
It's designed to be the mandatory evacuation window. Simple as that.
So if the BMS, the battery management system, detects the first signs of a cell starting to fail.
A sudden voltage drop, a
Yeah.
temperature spike,
Yeah.
it has to trigger a clear, immediate, loud, visible warning. And that 5-minute clock starts.
It's the minimum time calculated for the operator and anyone else on site to get out of the danger zone before that pack potentially vents hot gas.
Correct. But the real challenge, the one that keeps engineers up at night, is the proposed 2025 version.
GB 3031 2025, the mandate for zero thermal propagation.
Yes.
How do you even begin to guarantee that one failing cell won't cascade and take the whole pack with it?
It forces you to completely rethink design at the module level. You need two strategies working at the same time.
Okay, what's the first one?
First is directional vending. The battery housing has to be engineered with specific pathways, pressure relief valves. So if a cell does go, all that high temperature, high pressure gas is channeled instantly away from the other cells and safely outside the enclosure.
And the second strategy?
Advanced thermal barriers. This usually means putting aerogel insulation between the battery modules.
Aerogel, right. Incredibly low thermal conductivity.
Exactly. It physically and thermally stops the heat and fire from spreading from one unit to its neighbors.
Yeah.
If we design to that 2025 proposal now, we're future-proofing the product for the global market.
Okay, moving beyond thermal risk, let's talk functional safety. ISO 26262. For a heavy vehicle like this, working near people, what's the single biggest risk that gets the highest ASIL rating?
The highest rating, we're talking ASIL C, maybe even pushing to ASIL D, has to be applied to the most immediate mechanical hazard.
Which is?
Unexpected or uncontrolled rotation of that mixing drum.
I can see that. A worker is near the discharge chute, and that thing suddenly spins up to 15 RPM.
It's a catastrophic scenario, absolutely catastrophic.
So an ASIL D rating, what does that demand in terms of hardware? It's not just a software check, is it?
Absolutely not. To get ASIL D for torque control, you need a multi-channel safety architecture, a two-channel redundant system.
Give me an example.
So the vehicle control unit, the VCU, sends the torque command through channel A. But channel B, which could be an independent safety control unit, is constantly cross-checking that command against its own independent sensor inputs.
Like a second motor position sensor or a secondary current monitor.
Exactly. And if the main path, channel A, fails or commands something dangerous, channel B has to immediately engage a safety mechanism.
Like cutting the torque or just opening the main contactor.
Solve a torque limit, or yes, physically opening the safety contactor is a huge burden of proof.
So where does the high voltage interlock loop, the HVIL, fit into this safety hierarchy?
The HVIL is crucial, of course. It protects against electrocution, but it typically gets a lower rating, say ASIL B.
Why lower?
Because while protecting against electric shock is absolutely a life safety issue, preventing the immediate, uncommanded mechanical movement of a massive, dangerous part like that spinning drum,
Yeah.
that takes priority in the ASIL hierarchy for this specific application.
So the hazard analysis and risk assessment, the HARA, has to document all of this before you even pick a single component.
It has to. It's the foundational safety document.
We've set the safety context. Let's pivot to the power source itself, the 400-volt RESS. Our sources are incredibly firm on this. Lithium iron phosphate, LFP, is the mandatory chemistry. It even overrides the higher energy density you get from NMC. Why?
The decision comes down to two things: the operational environment and the total cost of ownership, or TCO.
Okay, we know LFP has a higher thermal runaway temperature, which is a big safety plus, but what about the environment?
Think about a construction site. It's dusty, there's heavy debris, there's always a risk of foreign object damage, maybe even a puncture.
Right.
If a catastrophic failure does happen, an LFP cell releases minimal oxygen when it decomposes. That drastically reduces the fire hazard compared to NMC, which releases its own oxygen. It's a critical life safety feature when you're working in a remote vocational setting.
And on the TCO side, the cycle life difference is just, it's staggering.
It is. A typical vocational vehicle, you expect it to last 10, maybe 15 years. LFP gives you 3,000 to 6,000 charge cycles. It'll often outlast the chassis itself.
Whereas NMC is closer to 1,500, 2,000 cycles.
Exactly. With NMC, you'd be looking at a very expensive midlife battery replacement, which just destroys the vehicle's long-term economic case. LFP is the clear winner for asset durability.
Let's get into the mechanical integrity. These mixers, they take a beating on unpaved surfaces. What specific tests does that ruggedized pack need to pass for the ISO 17753 standard?
That standard specifies the N3 commercial vehicle category, which is all about surviving random vibration and mechanical shock.
So we're not talking about simple, predictable vibration tests.
No, we're using random vibration testing. It replicates the completely unpredictable multi-frequency shock you get on a rough construction site. The pack has to withstand testing up to 10 G in all three axes for long periods.
And the enclosure itself has to be tough.
High-strength extruded aluminum or heavy-gauge steel, it has to maintain its structural integrity and its seal against water and dust for its entire service life.
You mentioned that a critical failure point isn't always the cell, but the internal connections fatiguing over time. You talked about using flexible bus bars.
Yes, this is a key engineering detail. The chassis rails and the battery housing, they're constantly flexing under that vibration. Just a little bit, but it's constant.
And if the bus bars connecting the modules are rigid,
They become stress concentrators, you get fatigue cracks, and eventually an open circuit right at the weld points.
so you use these flexible bus bars, often shaped like an omega symbol.
That's right, an EC or an inverted U. They're designed to absorb a few millimeters of movement between the modules without transferring that strain to the actual connection terminals.
So the engineering deliverable here would be what? An analysis report.
A finite element analysis, an FEA report, that proves the stress concentration at those connection points is reduced by at least 80% compared to a rigid design. That single detail is absolutely crucial for hitting that 15-year operational life.
All right, now for the brains of the operation, the battery management system. We need extreme accuracy in state of charge, SOC, to prevent what you called concrete hardening anxiety.
Chuckles, yes. You really don't want to run out of power mid-port.
So why is LFP's flat open circuit voltage curve the biggest challenge for an accurate SOC?
It's the trade-off you make for LFP safety. Between about 30% and 80% charge, the voltage is almost perfectly flat. A change of just 1 millivolt might represent a 10% difference in SOC.
So you can't just rely on voltage.
Impossible. And you can't just rely on counting the current going in and out, Coulomb counting, because small measurement errors and drift add up over time and become huge inaccuracies.
So this is where those advanced Kalman filters come in. How does an extended Kalman filter in EKF solve this problem?
It's an advanced state observer. It's not just counting charge. It relies on a very sophisticated equivalent circuit model, or ECM, of the battery.
And that model simulates the battery's internal behavior in real time.
Its impedance, its polarization effects, its internal resistance, all of it. The filter then takes the predicted voltage from that model and compares it to the actual measured voltage from the sensor.
And it uses the error between the two to constantly correct the charge count.
Exactly. The EKF is a bit faster because it linearizes the system, but a UKF, an unscented Kalman filter, can be even more precise. The end result is millivolt level accuracy, even with the high power pulsing you get from a P2 system.
Okay, that handles the short-term energy. What about long-term health, the state of health, or SOH? How do you track capacity fade over years of brutal operation?
SOA tracks two main things: the capacity fade, so how much energy it can hold, and the increase in internal resistance.
How it's getting weaker.
Right. For commercial vehicles, we often use a dual Kalman filtering approach. The first, fast filter, tracks the SOC in real time. The second, much slower filter, runs on a macro time scale, maybe hours or days.
And its job is to watch how those long-term parameters are changing.
Exactly. It watches how the internal resistance and capacity change slowly over the battery's life. This lets the BMS predict the end of life and tell the fleet manager when it's time to retire or repurpose that pack. It's a crucial financial deliverable for TCO planning.
And the state of function, SOF, that acts as the real-time throttle. What inputs drive that calculation?
The SOF is vital for safety and for the battery's longevity. It's dynamically calculating the maximum power you're allowed to draw or push in, based mostly on real-time cell temperature and SOC.
And the underlying physics is pretty straightforward, I guess.
It is. You drastically reduce power at low temperatures to prevent lithium plating, which is irreversible damage. And you reduce power to high temperatures to prevent overheating and thermal runaway.
And the BMS just broadcasts this limit to the VCU constantly.
every 10 to 15 milliseconds over the CAN bus. It ensures the VCU never, ever asks for a power spike that could hurt the battery.
Which brings us right to thermal management. Given the high ambient heat and the pulsing loads, air cooling is a non-starter, liquid cooling is mandatory. What's the key challenge there?
The challenge is uniformity. It's measured by the delta T, the temperature difference.
You need to keep the whole pack in that optimal window, say 15 to 45 degrees Celsius.
Right, but just flowing liquid across it isn't good enough. If the flow is uneven, you get hot spots.
Yeah.
So the critical design metric, which has to be validated by a CFD simulation,
Computational fluid dynamics.
is ensuring that the cell-to-cell temperature difference, the delta T, across the entire pack stays below 3 degrees Celsius.
Why is that 3-degree delta so critical?
Because temperature variation leads to uneven aging. The cells that are consistently even a little bit hotter will degrade faster, their capacity will fade quicker, their resistance will go up.
And that creates a weak link in the chain.
A weak link that prematurely shortens the life of the whole pack. So you need complex cooling plate designs with optimized serpentine flow paths to make sure you're pulling heat away from every single cell equally.
And if you're operating in freezing conditions, what does the BMS have to do to allow charging?
This is critical. If you try to charge a cold battery, you get lithium plating. The lithium ions basically deposit as metallic lithium on the anode surface instead of embedding into it.
And that's bad.
It's very bad. It permanently reduces capacity and can create dendrites, little metallic spikes, that can cause a catastrophic internal short circuit.
So the BMS has to prevent that.
The BMS must activate PTC heaters, positive temperature coefficient heaters, or circulate pre-warmed fluid before it allows any charging to happen. It has to get those cells up to at least 15 degrees Celsius before they can safely accept a high current.
Okay, we've covered the battery. Delivering that 400 volts safely requires, well, military-grade protection. Let's pivot to the electrical safety architectures, starting with the power distribution unit, the PDU.
Right, this is a key clarification. The battery is the source, but the PDU is the brain of the electrical safety system. It's the box that holds the main contactors, the pre-charge circuit, the fuses.
And the manual service disconnect, the MSD.
Exactly. The MSD is that big, physically keyed safety plug. It's mandated by regulations like ECE R100. It ensures that for maintenance or for first responders, you can create a guaranteed, visible mechanical break in the high voltage connection.
Understood. Now, the electronic monitoring of that connection, the high voltage interlock loop, or HVIL, what's its fundamental job?
The HVIL is a continuous low voltage 24-volt monitor. Its only job is to ensure the physical continuity of the entire high voltage path. It's your primary defense against a connector being loose or accidentally unplugged.
And the elegance is in that last mate first break principle. Explain the physical design.
It's a precision manufacturing detail. The main high voltage power pins are made just a little bit longer, maybe 5 millimeters. The auxiliary HVIL control pins are intentionally shorter.
So when you plug it in, the power pins connect first, then the HVIL.
Right. And when you unplug it, the reverse happens. The shorter HVIL pins break contact first. That gives the system a few milliseconds to detect the open circuit and command the main contactors to open.
Before the high voltage terminals are physically exposed and could arc.
Exactly. It's a simple but brilliant mechanical safety feature.
So, for diagnostics, why use a PWM signal on that loop instead of just a simple DC voltage?
It gives you much better diagnostic coverage. With a simple DC voltage, an open circuit is easy to spot. But it's hard to tell the difference between high resistance, say, a corroded pin, and a short to ground or a short to power.
And those are very different failure modes.
Totally different. By injecting a low-voltage PWM signal and analyzing the signal that comes back, the VCU can precisely distinguish between an open circuit, a short, and other faults. It dramatically increases the system's ability to self-diagnose reliably.
Okay, let's talk about the response logic. If an HVIL fault happens while you're driving, you can't just kill the power. What happens?
The VCU has to prioritize vehicle control above all else. If you're stationary, fine, it just inhibits high voltage startup. But if you're moving, you go into limp home mode. Immediately into limp home mode. That means a controlled, gradual reduction in torque over several seconds, combined with some very severe audio and visual warnings for the driver.
Because a sudden hard shutdown would be more dangerous?
Far more dangerous. You'd lose power steering, braking assist. You'd create a bigger hazard than the electrical fault itself. The system has to let the driver safely pull over.
Now, for the violence of high voltage startup, inrush current, why is just connecting the 400-volt battery to the motor control unit a recipe for disaster?
Because the MCU has these huge DC link capacitors inside. maybe 2,000 microfarads or more. They're there to stabilize the voltage bus for the inverter.
And when they're empty, they look like a dead short to the
A
battery.
dead short. You'd get a massive inrush current spike, potentially thousands of amps, that would instantly weld your main contactor shut permanently and bypass every single safety disconnect you have in the system.
Which is why the pre-charge circuit is mandatory. Let's walk through that.
It is. The circuit is basically a pre-charge resistor, let's call it RP, and a smaller pre-charge contactor sitting in parallel with the main contactor.
The VCU closes the small contactor first.
Right. It lets the resistor slowly charge up those big DC link capacitors to about 95% of the battery voltage. Only when the current drops, showing the caps are full, does the VCU command the main contactor to close, bypassing the resistor.
And the timing is all governed by the RC time constant.
Exactly. R times C.
The sources give an example. 400 volts, 2,000 microfarads, and you want to charge in half a second. That gives you a 100 ohm resistor.
But you said picking the component is more than just getting the ohms right?
Far more. That initial energy dump, even though it's fast, is massive. The engineer has to calculate the pulse energy that resistor is going to absorb. In that case, it's over 160 joules.
So you can't just use any old resistor. No. The component specified in the 0203 component selection report must be a high wattage ceramic composition resistor that is specifically pulse rated to absorb that energy. If you don't, it'll just blow out on the very first startup.
Here's a key risk question. Active discharge relies on the inverter to dissipate the bus voltage. But what if the inverter is what failed in the first place? Isn't that a single point of failure?
That's an excellent point, and it's a core principle of ISO 26262. The regulation mandates that the high voltage bus has to drop below 60 volts DC within 5 seconds of any shutdown or crash.
Because those big capacitors would hold a lethal charge for minutes otherwise, so you need redundancy.
You need redundant discharge paths. Active discharge is path 1. The MCU uses its IGBTs to burn off that stored energy as heat. It's fast, under 1 second. But as you said, it relies on the MCU working.
So it's path 2.
Passive discharge. This is the mandatory safety backup. These are fixed, high-value bleed resistors placed right across the capacitor bank. They're slower, but they guarantee that even if the VCU and MCU are completely dead, the voltage will still bleed down safely within that 5-second window.
And the high voltage schematic has to show both paths clearly.
Absolutely. It's a requirement.
What if something else goes wrong in the sequence? Let's say the pre-charge contactor welds itself shut instead of opening after the main contactor closes.
Another critical fault detection case. The VCU must keep monitoring the voltage drop across that pre-charge contactor, even after the sequence is done.
If it sees that the contactor is stuck closed.
It has to flag a severe fault. It will inhibit any future pre-charge attempts and probably trigger a main system shutdown to prevent the pre-charge resistor from overheating and failing. That level of detail has to be in the 0204 HVIL design guide and its fault tree analysis.
Okay, finally, the last line of defense, fuses. How do we coordinate them so a small fault in, say, the DC-DC converter doesn't kill the whole vehicle?
It's a layered defense, and it's all based on the I²T value, which is a measure of damage energy.
So you grade the fuses.
You grade them.
Okay.
The downstream branch fuses, the ones protecting the ePTO or the DC-DC, have a lower I²T rating. They're designed to blow faster than the main battery fuse upstream.
That way you localize the fault.
You localize it. If the main fuse blows first, the entire vehicle is dead in the water, which could be incredibly dangerous. The coordination curves have to be meticulously plotted.
For that main battery loop, the sources say we're moving away from old-school melting fuses to pyrofuses. Tell me about that technology.
It's a fascinating shift from passive to active protection. A pyrofuse is a pyrotechnic switch. It uses a tiny contained explosive charge to physically sever the current path.
So it's not waiting for a metal link to melt from heat.
Yeah, it's triggered electronically by the BMS or the VCU. It can be triggered by a crash sensor, or if the system detects a catastrophic internal short circuit.
And the advantage is speed.
Unmatched speed. A traditional fuse takes milliseconds to react. A pyrofuse activates in less than 2 milliseconds.
That's basically instantaneous.
Near instantaneous. And that's vital for protecting the very expensive battery pack against huge short-circuit currents up to 20,000 amps that could cause a fire. It's the ultimate non-resettable emergency stop.
We've specified the power source and the safety systems. Now let's get to the physical execution, laying this all out on the chassis, starting with the high-voltage harness layout and EMC.
Right. This is where the theory meets the gritty reality of a truck chassis. And the routing rules are strict for a reason. It's a high vibration, high heat, and electromagnetically very noisy environment.
All high-voltage harnesses have to be in that safety orange sheathing.
They do. And ideally, they should be routed on the inside of the frame rails to give them as much mechanical protection as possible.
What's the rule and separation between the high-voltage and low-voltage lines, and why is it so important?
It's all about electromagnetic compatibility, or EMC. The IGBTs in the inverters are switching power at high frequencies, which creates a ton of electrical noise.
And that noise can mess with the 24-volt control lines.
It can induce spurious signals in your CAN bus, your sensor inputs. It can cause chaos. So the rule of thumb is to maintain at least 100 millimeters of physical separation. 200 millimeters is preferred practice.
And if they have to cross.
They must cross at a 90-degree angle. That minimizes the area of electromagnetic coupling between them.
Okay, what about mechanical integrity? How do you stop these heavy cables from just shaking themselves to death?
Frequent and robust fixation. The large HV cables need to be secured every 200 to 300 millimeters with specialized anti-chafing clamps. And the clearance rules are absolute.
What are they?
You need to stay over 200 millimeters away from hot components, like the exhaust, which can cook the insulation, and over 25 millimeters away from any moving parts, like drive shafts, to prevent abrasion.
And even something as simple as the bend radius is critical.
It is. If you bend the cable too sharply, you can stress and crack the internal layers, the insulation, the shielding braid. The rule is the minimum bend radius must be greater than 5 or 6 times the cable's outer diameter. Violate that, and you're risking a long-term dielectric breakdown.
And how do we terminate the cable shielding to deal with all that high-frequency noise?
The shield is only as good as its termination. The cables must be fully shielded with a metallic braid. At the connector, that braid has to be compressed into a 360-degree circular ground connection to the chassis.
Creating a Faraday cage effect.
A highly effective one. It ensures that high-frequency noise on the shield is immediately shunted to ground so it can't radiate and interfere with other electronics.
Moving to component selection, deliverable 0203. We know we need PMSM motors for efficiency, but the ePTO motor is very specific because of what it's moving.
Wet concrete, which is
Right.
heavy, sticky. The static inertia must be incredible. It is. The ePTO motor has to overcome the static friction and inertia of a drum full of tons of material. This means it needs an extremely high starting torque capability, often 3 times its nominal rated torque.
Just to get the drum to break loose without tripping the overcurrent protection?
Exactly. It requires very careful selection of the motor's control strategy and its base speed curve.
For the contactors, why the specific requirement for gas-sealed DC contactors?
Because DC arcs are much harder to extinguish than AC arcs. AC naturally goes through a zero crossing point, which helps kill the arc. DC doesn't.
So when you break a high-voltage DC connection under load, you get a plasma arc.
An arc that can sustain itself and just melt the contacts. Sealing the contactor chamber and filling it with an inert gas, like hydrogen or nitrogen, creates a low-oxygen environment that rapidly extinguishes that arc. It gives you the superior load break capability you need for emergency switching.
And the DC-DC converter, what's its role when the engine is off during mixing?
The DC-DC converter is the lifeline of the control system. The 24-volt system runs everything: the VCU, the ePTO controller, the cabin controls, all the safety sensors.
And when the engine's off, the alternator is offline.
So the DC-DC, usually a 3 to 5 kilowatt unit, acts as the bridge. It continuously pulls stable power from the 400-volt bus to keep the 24-volt battery charged and all the control electronics happy throughout the entire mixing phase.
Let's dedicate our last few minutes to the critical documentation that proves this all works. The blueprints the executive needs to sign off on.
These are the documents that turn a concept into a certifiable, safe product. First, 0201, the high-voltage schematic. This is the master document.
It maps the entire power flow.
From the battery through the PDU, showing every fuse, every contactor to every high-voltage load. And crucially, it has to define all the isolation monitoring points and voltage thresholds for maintenance crews and first responders.
Then, 0204, the HVIL design guide. This is the safety rulebook.
Correct. It defines the precise logic, the diagnostic thresholds, everything. But the core deliverable inside this document is the comprehensive fault tree analysis, the FTA.
And the FTA does more than just list faults.
It charts specific fault chains. For example, it will link a short-to-ground fault on the HVIL with the required secondary response, like disengaging the K0 clutch, and the tertiary failure mode, like a full system shutdown if the vehicle is below a certain speed. It ensures a predictable, safe response for every conceivable failure.
Finally, the communication spine. ZO205, the BMS interface, and CAN matrix.
This defines how the 400-volt brain talks to the 24-volt chassis. It's mandated to follow the heavy-duty SAE J1939 standard.
And the CAN matrix lists every critical piece of data the BMS broadcasts.
Every single parameter group number, or PGN. Beyond the basics like SOC and voltage, the most critical broadcast is the operational limits, the SOF, the maximum allowed charge and discharge power.
So the VCU is programmed to never ask for more power than the battery says is safe at that exact moment.
Never. And any safety alerts, like a thermal runaway pre-warning, have to be communicated using high-priority DM1 diagnostic messages for immediate system action.
To wrap up, let's look at two specific, really clever features that show the sophistication of using an electric motor to handle concrete. First, dynamic torque compensation.
This addresses the reality of the load. As the truck accelerates, brakes, and turns, the wet concrete inside the drum sloshes around. It's called load migration.
And that changes the torque needed to keep the drum spinning at a constant speed.
Dramatically. Dynamic torque compensation uses sensor fusion motor speed, current, maybe vehicle roll sensors, to constantly adjust the motor torque and maintain that steady 5 RPM, for example. That stability is critical to keeping the concrete properly mixed.
The electric motor also acts as a very precise sensor. Tell me about digital slump monitoring.
This is a huge value add. Traditionally, checking the concrete's consistency or slump is a manual process. Here, the ePTO controller constantly monitors the torque ripple and the average current needed to turn the drum.
And that data correlates directly to the stiffness of the concrete.
Exactly. The algorithm can give the operator real-time feedback on the material's consistency, allowing for on-site adjustments and preventing a very costly delivery of bad concrete.
And finally, rocking logic. What happens if there's a blockage?
Blockages are common, especially buildup near the discharge chute. If the controller detects a stall, it automatically executes the rocking logic.
Which is?
It's a controlled sequence of high-frequency, high-impact forward and reverse switching. That oscillation generates just the right mechanical shock to break up the blockage without overloading the motor. It's a massive improvement in uptime.
So we've done a truly rigorous deep dive here. We've defined the 400-volt P2 hybrid cement mixer architecture. We've integrated mandatory safety from the ACEL-rated HVIL to the Pyrofuse, with critical durability standards like ISO 16753 for vibration.
And the strategic value is just undeniable.
Yeah.
By decoupling the engine and letting the ePTO handle stationary mixing, the economic returns are immediate and they're quantifiable. We're seeing fleet-wide fuel reduction of 30 to 50%.
Which improves TCO and hits those global emissions targets at the same time.
Exactly. And the O201 schematic and the O204 HVL design guide, those are the executive-level documents that guarantee the integrity of this entire system.
It's amazing to think that 40 years ago, that drum was run by a chain, then hydraulics, and now it's all sophisticated electronics. As the industry looks towards 800-volt platforms, what's the key difference between that future and the 400-volt standard we've discussed today?
Well, the main advantage of 800 volts is really efficiency at scale. You can deliver the same power at half the current, which means smaller, lighter cables and much faster charging. But for this current generation of vocational trucks, 400 volts is a mature, cost-effective, and standardized ecosystem.
So the complexity isn't really the voltage level.
Not really. The real complexity is in the intelligence. The intelligence built into the BMS and the VCU to manage safety and energy dynamically, no matter what voltage you choose.
The ultimate takeaway here seems to be that electrification forces a total system redesign. So for the engineering executive trying to finalize this project, what is the fundamental safety question they have to resolve before they move to production?
The fundamental question for that safety executive remains this. In a heavy vocational machine, where failure risks human life and massive material loss, which catastrophic risk the immediate functional failure of your control system or the long-term slow-burn mechanical fatigue of your structure, which one should command the highest ASOL rating in your final design validation?
Hardware durability versus immediate functional control.
That prioritization defines the entire safety philosophy of your organization.
That sets the priorities perfectly. Thank you for walking us through this incredibly detailed and rigorous technical specification.
It was my pleasure.
And thank you for joining us on the deep dive. We'll see you next time.